Okay, so let's look at these. Got two more here. I want to draw the shear force and bending moment diagram, and we have, again, two cantilevers, one that has a uniform load, and then one that has a linearly varying load. So again, just to help us get started, I'm going to go ahead and give you an idea of what these reactions would be. First, you'll notice that if we take the concentrated equivalent of this distributed load, it would land right here in the center. It would have the equivalent force would be the same as the area under the curve. So base L times height W naught. So I've got W naught L as the load, and it happens right in the middle. So that would be L over 2. So if you sum forces in the y direction, hopefully you'll see that the shear over here on the left side is W naught over L. And that the moment, when you compute it, would be W naught L squared over 2. Basically the force times the distance, and this in the opposite direction. So what kind of shear force is this to start with? Positive or negative? Positive. What kind of bending moment is this to start with? Positive or negative? Negative. So if I go down to my shear diagram, I'm going to start with a positive shear of W naught times L. What's the shear out here on the free end? There's no applied force, so it must be 0. So again, let's remember our relationships that we've been using. So we know that the change in shear is the area under the load curve. And then that the slope of the shear diagram is equal to the load. So let's first start with this one, the integral relationship. So you'll notice that the load is continuous to this whole section, so the change in shear from the left side to the right side should be equal to the area under the curve. And what's the area under the curve? W naught times L. By the way, what kind of load is this? Is this a positive or a negative load? It's negative. So the change should be negative W naught over L. So if I start at positive W naught over L and add the change, which is negative W naught over L, I do get 0. So that seems to work. And it says the slope of that curve is equal to the load. And what is the load? Well, it's W naught everywhere, right? It's constant. Is it positive or negative load? It's negative, so it should be a negative slope. In fact, if I marked it, the slope would be negative W naught to 1. And I get a shear diagram that looks something like that. That's a 0, by the way. Any questions about that? So where's the maximum shear? At the fixed connection, and it's equal to W naught L. All right, let's look at the moment. Looking at the starting point, I go back up here. Do I know something about the moment when I start? It looks like it's W naught L squared over 2. Is that positive or negative bending moment? That is a negative bending moment. So that should be negative W naught L squared over 2. What's the moment at the free end? 0. So let's see if that works. So this should be satisfied by the relationship that the change in moment is the area under the shear diagram, and that the derivative of the moment is equal to the shear. Oh, you guys know why the integral sign looks like that? It's an elongated S. And what is S for? Summation. So it's just you're summing up all the little v times dx's there are over that limit. Isn't that cool? I don't know if that's true or not, but it makes good sense. So let's do that. So the area under the shear diagram should be the change in the moment. What's the area under the shear diagram? Well, it's a triangle. And it is 1/2 base L times height WL. You multiply that, you get WL squared over 2. And this is a positive area, so it's a positive change. So if I start at negative W naught L squared over 2, add W naught L squared over 2, I do get 0. Very reassuring. Now what is the slope of the moment diagram? Well, it's equal to the shear. Is the shear constant? It is not. What is the shear here at the beginning? It is equal to W naught, and it is a positive value. So I'm just going to come down here and indicate that I've got some kind of positive shear going on. And that value is decreasing until it gets to be what? What's the shear there? 0. What's 0 slope? It's a horizontal line. So that means my curve needs to start with this slope, positive slope, and decrease to 0. And this is where the qualitative part comes in, because you're just going to sketch a curve that somehow looks like that. Is that the exact shape? No, but it has the characteristics of the curve in that you know the beginning point, you know the end point, and you know its shape. So what's the maximum moment in this structure? W naught L squared over 2. It's negative and occurs to the fixed connection. So we started off with a constant value. We integrated that, got a linear line. We integrated that. This is actually a second order curve. So we talked about n. This would be n1, and this would be n2. So this is actually a quadratic curve. Do I actually know the quadratic curve? I do not. I have not derived the quadratic curve. But I do know endpoints, and I know its general shape. And that's good enough for this, because again, we're just trying to pick off where the maximum moment occurs and its value. We've got that. Where the maximum shear occurs and its value. We've got that. So it solves our problem. Let's try this guy. So the same thing is true. I'm going to come up here at the beginning, and I'm going to get a concentrated equivalent for this loading. So it's triangular, so it's going to be 1/2 base L times height W naught. So that should give me W naught L over 2. And then from the fixed connection, what's the distance to the centroid? It's 2/3 the length, right? So this distance is going to be 2L over 3. Now I'm confident that you could do the statics and find the reactions, and that when you do that, you would find that the shear is up and equal to W naught L over 2, and that you would find a moment that looked like this that would have the value W naught L squared over 3. Okay? So now that I know my reactions and I have my loading, I can construct the shear. So starting here at the left side, what's the shear at the beginning point? Looks like it's W naught L over 2. What's the shear at the free end? It is 0. So the change in shear between these 2 points is what? The area of the load curve. What's the area under this load curve? What's a triangle? 1/2 base times height. But the height in load terms is negative. So you'll get negative W naught L squared over 2. So again, positive W naught L squared over 2 times the change gives you 0. So that's the right, that looks good. So now what's the shape? Well, the shape is equal to the load. So starting here, what is the loading at that point? I go up and the loading is what? 0. So that means my slope of my line there should be 0. And as I move, what happens to my slope? It's linearly increasing to a maximum value here of W naught. And is it positive or negative? It is negative. So that means I have a big negative slope. In fact, if I marked it at that point, it would be 1 to minus W naught. You see that? So even though I don't know the exact how the curve behaves, I do know its qualitative shape again. It's going to look something like that. So there's the variation of my shear. Again, as a structural engineer, all I care about is where's the maximum shear. So you look at the curve, maximum shear is right there. W naught L over 2 occurs at the fixed connection. So I started off here. This curve is order 1. So this curve is order 2. What's the moment going to be? Order 3, which means it's going to be cubic. All right, let's look and see what we know about the moment. So at the starting point, I go up, and what is my starting moment? Looks like it's W naught L squared over 3. Is that a positive or negative bending moment? Negative. I'm going to start off at minus W naught L squared over 3. What's the bending moment at the free end? 0. So this relationship, the change in moments here in the shear diagram, ought to give me this change. Now comes a little bit of a challenge and maybe a disadvantage of using this graphical technique, is you'll now notice that I need to find the area in the shear diagram, and what shape is the shear diagram? It's quadratic. You guys know the area of your quadratic curve off the top of your head? I happen to know this one, but not in general. So if you do have a 0 slope at the start, this is called a parabolic section. And the area of a parabolic section is 2/3 base times height. If you don't know that, I would encourage you to look at the front of your book, or maybe it's the back. It's the back. So let me slide this in here real quick. Here's your book, and you'll see areas and centroids of shapes, and the one that we're doing right now is this one. So if you slide over here, you can see, it's hard to see, but it is 2/3 base times height. And then this is for any in-order segment. And it gets a little more complicated. But that's probably going to be the limit of what we can do. So this is a small disadvantage in this particular application. But I do know that. So what is the area? 2/3 base times height. So it's 2/3 L times W naught L over 2. And when you calculate that, that comes out to a positive value of W naught L squared over 3. So you add that to this value and you do get 0. So that does seem to work. So what's the shape of this curve? Well, the slope at every point is equal to the shear. So let's start here at the left side. What is the value of the shear? It's positive. So I'm going to draw a positive slope, and it decreases to 0. So this should be a 0 slope. So again, if I fit those, I get a general shape, qualitative shape for my moment diagram that looks like that. So ultimate question, what's the maximum moment? Where does it occur? The maximum moment is negative bending moment, W naught L squared over 3, occurs at the fixed connection. Questions about those? We're going to do quite a few more.